Hello, good people of the internet. Welcome to our second recording. We are continuing with our routing series, and today we are going to look at OSPF. We're going to start with the OSPF basics because OSPF is a complex routing protocol. We're going to start with the basic, and then we are going to progress with our future videos up to a level where we'll be comfortable managing an OSPF network, deploying an OSPF network, or even taking an exam. So let's get started with OSPF. Today we're going to look at the basics in Huawei routing. So OSPF stands for Open Shortest Path First. Open Shortest Path First. So today we are going to describe the working mechanism of the OSPF. The working mechanism of OSPF is anchored on 3 steps. One step is neighbor discovery. The other one is link state, then followed by link state information exchange once the routers discover each other as neighbors. And then from the link state information exchange, they calculate the best path. And the best path is installed in the routing table. The best path is installed in the routing table. So we're also going to look at how to configure basic OSPF for only single area. We're going to see that in future videos that OSPF is in hierarchies. We have hierarchies where we have area 0 as the backbone. So for today, we are only going to look for one single area, and then we're going to look at some verification some commands for verifying the configurations. So let's start. So once you have your network topology, you have the basic connectivity, you have issued IP addresses on the interfaces, then for example, you have enabled OSPF on this router B, router A, router C, and router D. So we're going to see how to enable. But now we are looking at the working mechanism. So once OSPF is enabled, what the routers do is that they establish neighbor relationship with each other. So router B will establish a relationship with router A, and router A will establish a relationship, a neighbor OSPF relationship with router C. So the first step is neighbor discovery, that router A will discover router C and its neighbor, and also router B as its neighbor. So once that one is established, they exchange what we call link state information. So router A will have some link state information that will send to B. How that one works is that it will exchange. You see, we have a link state advertisement to link A, to router B, and the router B as well advertises the link state information to router A. So router A will also send a link state information to router C because it's a neighbor. Router C is a neighbor. So it will send a link state advertisement to router C. This link state advertisement that is sent to router C also contains the LSA router A received from router B. This link state advertisement sent by router A to router C also contains the link state information that was received from router B. So similarly, router C will send a link state advertisement to router A, you see. And so also router A, when sending link state advertisement to router B, it will include that link state advertisement it received from router D. So this is what is called a link state information flooding. It is flooded because this link state information from this router A will finally reach router B through router A. So because of that, the link state information is sent to a multicast IP address. So when this one is sending data, link state advertisement, it will send either to this of 2 IP addresses, multicast IP addresses, depending on the network topology. We look at the network types in OSPF, but this is the multicast IP addresses that are used by OSPF. 224.0.0.5 for all OSPF network to sending to all OSPF routers. So this one, if it wants to send link state information to this and this, it will send to this particular IP address. They'll all receive it from here. But if there was a DR or a BDR and wanted to send data to it, it will use this multicast IP address. So I've seen exams asking which IP addresses that are used by OSPF. So these are the IP addresses that OSPF router sends information to. So once we have the link state information flooded, so that every router will receive link state information from every other OSPF router, each router will build what we call link state database from that information. So once this one received LSA link state advertisement from router A, it will build a link state database. So every router will build a link state database. You can see this one has built a link state database. And this link state database of B contains link state advertisement of A, link state advertisement of B itself, link state advertisement of C, and the link state advertisement of D. Why? Because when this one send its link state advertisement to RTC, RTC also send its link state advertisement to RTA. And in that link state advertisement, it also contained the link state advertisement it receives from D. You see? So when this one also sends to RTB, it will send its own link state advertisement plus all the link state advertisement it has received. So eventually this RTB will have all within that area. Within that area, we'll have the link state advertisement of all the routers within that area because it's flooding. So that's what we are saying. Every OSPF router in an area have a similar link state database. We are going to look at that from the configurations. So I hope we have understood the mechanism up to this far. We have, once the neighbor relationship is established, the routers exchange the link state advertisement. The link state information is flooded. And each router from the link state information, it builds a link state database, each router. And what you're saying is that every router in a link in an area, every OSPF router in an area have a similar link state database. That's what we are saying. That's the most important and very critical for us to understand the working mechanism of OSPF. So because every router has a link state database, it uses that link state database and runs an SPF algorithm, or what we call shortest path first algorithm, and works out a shortest path tree. This is a shortest path tree, not to be confused with spanning tree. It's the shortest path tree whose root is the router itself. So let's assume this is router B that is doing an SPF algorithm. The root of that spanning shortest path tree will be router A, and works out the best route, calculates the best route to various destinations. From the shortest path tree, it calculates the best path to destinations. And those paths are then installed in the routing table. And then we'll forward data depending on the information on the routing table. So the first thing is neighbor relationship, flooding of link state information, building of the link state database, and then from the link state database, we run SPF algorithm, shortest path first algorithm, to create a shortest path tree from which we'll calculate the best routes, and those best routes are installed in the routing table because we forward data based on the routing table. So the final process is to get the best routes into the routing table. I hope that one is clear, so that before we start our configurations, we have to get that one clear because our configurations will be based on that. So let's start our configurations and see all this in action. So I have a network, just like the one I've used in the slides, no more slides now. I have a network, I have router A, router B, router C, and router D. I've done the basic configurations so that this one I've given it an IP on this interface, G01, G00, and 01. And this one the same, I've given it the interface on that, I have given it an IP, and this one as well. So for now, we are going to use these three of them. So let's start with router 1, router A, and let's see whether we have those configurations. So we can display IP interface brief. Sorry for this, we need to do this command so that it do not have, sorry, and terminal monitor so that we do not have those log messages coming through. So let's clear this. Display IP interface brief. So you can see already G00 has an IP address and it's up. G00, this one, it's 192.168.0.1.1 on this side, .2 on this side. And we also have G01. G01 is 172. G01 is this 172.16.1.1 on this side. And also we have a loopback. We have a loopback IP address, which is 1.1.1. So the first thing when you're configuring OSPF is you first the first thing is you configure the router ID. That's the first thing. It's not mandatory, but it's best practice. It will save you a lot of configuration headaches. And when you're verifying your configurations, it makes it easy for you to identify your topology. So the best practice is to give the router ID your loopback 0 IP address. You give it as your router ID. So in our case, our loopback 0, we display IP, we display current interface loopback 0, we see it has an interface IP of 1.1.1. So you can say router ID 1.1.1. That is the first step. Then the second step is to configure your OSPF. So the command is OSPF. If you question mark, it will give you, one of the things it will give you is the process ID. So for our case, we can say it's process 1. And then the next thing, if you question mark, you'll see the next thing we are going to do is to declare the area that we are configuring for. In our case, we are configuring everything is in area 0. As you can see from here, this area 0. So we are going to say area 0. That's the second thing. The third thing is to enable. We have to enable the interfaces for for OSPF. The OSPF will not work unless you have enabled the interfaces for OSPF. So how do we do that? We do that using a network command. Is something called a network command. So if you do network, the word network, and you question mark, let's question mark and see what network gives us. You see, network tells us enable routing on an IP network. This is a network command we use to enable OSPF on the interfaces. So we can do network. And if you question mark, it tells you to give it the network number. The network number is basically the IP address. So the network, not the network IP address, is the network IP address, not the interface IP address. So this is the network IP address, 192.168.0.0. That is the network IP. Remember, when you subnet, you normally have the network IP address and the broadcast IP address. So what you're required to input is a network IP address. So the network IP address for this is 192.168.0.0. So we put that one as our network IP address. Then what does it tell you next? It asks you for, sorry. It asks you for OSPF wildcard bits. What is wildcard bits? Let's look at an IP address. An IP address, like a network, our network IP address is 192.168.0.0. And we have seen from our previous lesson that an IP address must have a subnet mask. And we are saying the subnet mask for this is stroke 30. So the network mask is stroke 30. In long format, that subnet mask, the subnet mask is 255.55.255.252. If we write it in bits, it will be 11.11.11.11.11.11.11.11.11.11.11.00. So what wildcard bits are? Wildcard bits are the opposite. So let's have wildcard bits are the inverse of the subnet mask. What does that one mean? What does that mean? Where there is 1 in the subnet mask, we put 0. And where there is 0 in the subnet mask, we put 1. So if you do that, this one will be 8 zeros, 1, 1, 1, 1, 1, 1, 1, 1, dot, 1, 1, 1, 1, 1, 1, 1, 1, dot, 1, 1, 1, 1, 1, 1, 1, 1, dot, 1, 1, 0, 0, 0, 0, 0, 0. Then where there is zeros, we put 1, you see? So that one becomes a wildcard bits. But they want us to write it in decimal. It's normally in decimal. So if we convert these zeros to decimals, it will be 0. If we convert this second octet, all the zeros will be zeros. The third octet will be 0 as well. But the final one will be, this one will be 3. So our wildcard mask is 0.0.3 for last stroke 30 network. So maybe for your homework, what would be the wildcard mask? Calculate wildcard mask for la stroke 22 network. So that one is for your homework. You can give your response in the comments below as you subscribe. But you have understood, I hope you have understood how we calculate the wildcard mask is that we write the long format of the subnet mask. We write it in bits. And then where there is 1, we put 0. And where there is 0, we put 1. Then we convert the outcome to decimal. That's how you get the wildcard mask. So the wildcard mask for our network is 0.0.3. So we continue with that. So 0.0.3. If you display this, it will show you the configuration under that area is that you already have added one network, you see. So let's clear this and continue. We also need to add this network, the network that is facing router C, which is 172.168. So you also need to add that one. So network 172.16.1. The network IP address is .0. So it's not the interface IP address, it's the network IP address. And the subnet mask is also a stroke 30. So it's 0.0.0.0.0.3. So if you display this, we now have two networks. We also need to add our loopback so that we are able to test our connectivity. So our loopback is 1.1.1. The network is 1.1.1. What is the wildcard mask for it? If we display current interface loopback 0, we are saying that the wildcard, the mask is 255.255.255. Meaning every bit is 1. So if all those bits we convert them to 0, we result with 0.0.0.0. Okay, so we put network 1.1.1 is our target network, and the wildcard mask is 0.0.0 because the mask, everything is 1. In the mask, everything is 1. So we convert that one, the inverse will be 0 for all of them. And if we convert back to decimal, there will be 0.0. So if we display this, you now see we have our 3 network. So at this point, it's good to, for point-to-point, we'll talk about this later in our advanced lessons. For point-to-point, you can see this is Ethernet, but it's point-to-point. It's only connecting to another router. There is no broadcast network here. There is no something like a switch. It's only connecting to one and only one other connection. So for such particular kind of network and Ethernet is involved, it's a good practice to do this command. We'll talk about this command later. OSPF network type point-to-point. We'll talk about it later. So for now, we just configure it. So now we have finished our basic configuration for OSPF for this router A. So our first verification command is to see which interfaces have been enabled for OSPF. And that command is display OSPF interface. And you can see we already have 3 interfaces. 192.168.0.1 is there. It's here. It's enabled. And then 172.16.1.1. 172.16.1.1 is enabled. And they're telling us it's a point-to-point. See, it's a point-to-point network. Sorry, pointed is the wrong thing. It's a point-to-point network. And also our loopback appears, you see. And then if we head up, we'll talk about DR and BDR later. You'll see where they come to play. But here we are not having a broadcast network because we did this command. We prevented that broadcast network. So we're not having any DR or BDR. We'll talk about these ones later. What is important for this command is to tell us the interfaces that have been enabled for OSPF. Great. So let's now, with that, for it to work, remember our processes is 1, establish a neighbor relationship. So we have to configure another neighbor. So we have to configure router A to be a neighbor to RTA. So you see, so let's come here and let's undo terminal monitor here so that we do not have those synchronous messages coming through. We clear this. So remember the first step is to configure the router ID. So we start with router ID. Let's see what is the interface loopback configurations for this so that we use the same. So router ID, name it 2.2.2 because that's the first step to give our router an ID, and then OSPF. Remember, we say OSPF, then process ID. Which process ID we give here? The same process ID we gave on this router, you see? So the process ID here is 1. So here we also do process ID 1. And then the next thing is to declare the area. For everything you're configuring is on area 0 for this matter. And then we enable our network. The first network to enable is this one that is facing to router A. So we do the network IP is 192.168.0.0. So network 192.168.0.0, and then wildcard mask is still .30, so .3. And we also, on this side, we are not enabling this interface. So we will not add this network. You see, we will not add this network because you're not enabling on this interface. So we say network. The loopback was 2.2.2, and everything in the subnet mask was 1. So will be 2.2.2 and then 0. If you convert the subnet mask into wildcard, you'll get 0.0.0. So if you display this, it will show you have added those two networks. So the next item is, remember what we said about point-to-point. So we enable here, we say OSPF network type point-to-point. So the first command, we display OSPF interface so that we can see the interface that have been enabled for OSPF. And we have now 2 of them because we have enabled for this and we have enabled for the loopback. We have not enabled for this. I hope that one is clear. So we'll only run OSPF on the interfaces that have been enabled. So even though this router is configured for OSPF, there is no neighbor relationship on this side because this network has not been enabled for OSPF. So we only have 2 interfaces, this interface and the loopback. This one is not enabled for OSPF. So that is the first command for verifying. So the second command for verifying, remember our processes are establish neighbor relationship, then flag link state information, and then use that one to calculate the best route to the destination. So the first command, the second command will show us the neighbors that we have, the OSPF neighbors that we have. And it say called DS display OSPF peer brief. So you can see from this router that we already have a neighbor on G00, you see. On G00, we have a neighbor. And that neighbor, its ID, remember we configured the router ID. Its ID is 1.1.1. Let's verify whether that is true. Let's say display router ID here. You see the router ID is 1.1.1. So this is the router ID. So the router ID of RTA1 is 1.1.1. So this one tells you that we have RTA, router A is our neighbor, and the state is full. We shall look at this later, but you're seeing there is a neighbor. So if you come to RTA, the same, we should expect the same. We display OSPF peer brief. It has a neighbor, and that neighbor, its router ID is 2.2.2. Are we clear on that? So we have our neighbor. What was the next step? The next step, so they have now, because they are neighbors, they have exchanged link state information, and we expect them to have built some link state database. So that command is for displaying the link state database. So we can say display OSPF LSDB. If you question mark ls, let's say question mark. Let's question mark so that you can see what LSDB stands for. There is here, it's here. Link state database. So let's see the status of the link state database. So link state database. And you can see this router, router B, has two. It has two LSAs in the link state database. So it has for router A, and for itself. You can see that. See, for the router A, we said the router ID is 1.1 and itself it's 2.2.2. We expect also router A to have the same. So display OSPF LSDB, because we said routers in the same area have similar database, link state database. You see, we have the same, the two routers for router A and for router B. For router A itself and for the router A that it received from router B. I hope you are clear on that. So now let's add a third one. Let's add this one to the whole configuration, to the OSPF process as well. So undo terminal monitor. So sees. So the first, let's see the interface here. Loopback 0. What is the IP address for the loopback 0? It's 3.3.3. So sorry. So the first step is to configure the router ID. So best practice is to follow the IP address on loopback 0. And then we go to OSPF. OSPF process is still process 1. Remember, we are keeping consistent. And then we define our area. Everything is still in area 0. Everything is still in area 0. So we give area 0. And then we need to enable OSPF on this interface for this network and for this network and the loopback. This network, and the loopback. So we start with this network. So we say network 172.16.0.1.0, 0.0.0.3. And then for this network is 172.31. So network 172.31.1.0. Still, the world record mask is the same because they are both /30/30 IP addresses. And then also enable our loopback. Our loopback was 3.3.3, 0.0.0.0. And then because of the best practice, we go to G0. I think this interface is 0.1. Yes, 0.1. OSPF network type P2P. And then the other one is 0/3. So we repeat the same command. And then the first thing is to display interface, OSPF interface, so that we can see the interfaces that are enabled for OSPF. We have for this network, this interface, and this interface 16.1, this interface on this side. And we also have our loopback. So the second command is to check our neighbors. Display OSPF peer brief. We have a neighbor already here. We have a neighbor on this interface, and it's 1.1.1. See, the router ID of the neighbor is 1.1.1. That tells you it's RTA. So RTA is our neighbor. Why is it that we don't have a neighbor on RTD? A good question. Why is it that we don't have a neighbor on RTD? It's simply because this router has not been configured for OSPF. If we had configured it for OSPF and enabled this interface for OSPF, we would have it as a neighbor. But for now, we don't have a neighbor on that side because this one is not configured for OSPF yet. So only this one is configured for OSPF, and this one, and also this network added. The same case here, we do not have a neighbor on this side, because even though OSPF is configured here and OSPF is configured here, this network has not been enabled for OSPF. Are we together on that? That's why we do not have a neighbor. This RTC does not have RTB as its neighbor, because this network has not been enabled for OSPF. That one should be clear, because it's very important when we come to troubleshooting. So we have a neighbor. If we go to RTA and display the neighbor, we expect it to have two neighbors, because this one has been configured for OSPF and that network has been enabled for OSPF. This one has been configured for OSPF and this network has been configured, enabled for OSPF. So we expect it to have two neighbors, RTB and RTC. So display OSPF peer brief gives us the two neighbors, you see, 2.2, that is B, router B, and 3.3, that is router C. If you come to B, should have only one neighbor, because even though this one is configured for OSPF, this network has not been enabled for OSPF. So two levels, if you're troubleshooting an OSPF network, look for two things: whether the router itself has been configured for the OSPF, and the concerned network, whether it has been added to the OSPF process using network command. So those two conditions have to be fulfilled for it to have a neighbor relationship. All right. So it only has, if we display here, display OSPF peer brief, it only have one neighbor, which is RTA and not RTC, because this network has not been added to the OSPF process. I hope that one is clear. So if now we display the LSDB, let's see how it changed. We had only two routers earlier. Now we have added a third router. Let's see whether it will reflect here. So if we display, we can recall that command. You see, we have now three routers. We have router B, this router itself, and then router A is 1.1, and router C, you see. And if you can look at the edge, router 2, router B, is the one that has been there the longest, followed by router A, LSA, and router C is our latest addition. You see, it has the least time in the LSDB. So it has three of them: router C, router A, and router B. So let's look at router A that has the same. So if we do display LSDB, it also has the same three routers: router C, router A, and router B. And the same, router B has been the longest here, router A followed, and then router C is our latest addition. You can say that. So if you go to router C, we expect it to have the same display OSPF LSDB. Display OSPF display OSPF LSDB has the same, you see. So because this one verifies that all the routers in the same area will have the same link state database. All of them, because we have seen this is C has the three routers, router C, router B has the three routers, and router A has the three routers as well. So that is the concept, and that is the key takeaway for today's lesson. So now from RTC, we can see whether we are able to reach this loopback. First of all, The fourth command is to verify the routes you are receiving via OSPF. So you can say display OSPF route, routing table. So you can see we are receiving all these routes through OSPF. At router C, we are receiving 3.3. We are receiving 1.1. We are receiving 2.2, the loopback of the others. So you see, we can receive that one. We can receive even this network that is remote to RTC. Remember from our static routing lesson, we say this route by default, this router by default only knows about the directly connected network, but does not know about a remote network like this one. But now in this case, through OSPF, we are able to learn about that network through OSPF. So if you say display IP routing table, you see now what we have in the routing table is that we have 1.1 that we are running through OSPF, because 1.1 is not directly connected to this. So by default, this one does not know about 1.1. But because of OSPF, it can now know about 1.1. You see here, 1.1. And then about 2.2. This one about the loopback here, knows about it. And also 10.10 because it's directly connected to it. And 127, forget about that. And this 172 is directly connected to it. But this one is not directly connected to it. You can see that. This one is not directly connected to RTC. So RTC will never know about this network unless you use either routing, either static routing, or in this case, use OSPF. So by OSPF, we have learned about that network. And we can actually ping it. So 192.168.0. maybe 2. And it goes through because we can learn that route through OSPF. So the best routes have been, so that is the basic operation, working mechanism of OSPF. In our subsequent lessons, we look at the hierarchy of the areas, the area types, and the LSA types. Thank you for watching, and keep tuning and subscribe so that you can get notification when we release other videos like this. Thank you very much and have a good day.